Okay, friends. Let us derive the expression for energy of electron in Bohr's orbit. So, say we have an electron which is revolving in some nth orbit around the nucleus at a distance rn with some velocity vn. So, it will have some energy because it is revolving with some velocity, it will have a kinetic energy. And since the electron is placed in the potential of nucleus, it will have some potential energy. So the total energy of the electron will be the kinetic energy plus the potential energy. Let us first discuss the kinetic energy. Now, using the Gauss first postulate, we can very easily arrive at kinetic energy because we know kinetic energy is half mv square. I already see the mv square term here, right? So what I can do is simply cancel out the Rn with the square term here. That leaves me with mvn square that is equal to 1 over 4 pi epsilon naught z e square over Rn. Now, I know that kinetic energy is half mv square. What I have is only mv square. So I can simply multiply half on both the sides. This will be half mvn square equals 1 over 8 pi epsilon naught z e square over Rn. Now, with the help of this, I already have my kinetic energy. Since this half mvn square is nothing but my kinetic energy. So I have got the kinetic energy that is equals to 1 over 8 pi epsilon naught z e square over Rn. So now let us discuss the potential energy. Now, in order to discuss potential energy, first you should know that since this electron it is revolving since this electron is revolving in the potential of the nucleus, the electric potential of the on the electron due to the nucleus is given by 1 over 4 pi epsilon naught z e over Rn. So what is the potential energy then? The potential energy of the electron will be given as, say, PEN. That will be simply the electric potential that the electron is in times the charge of electron, which is minus E, since electron is negatively charged. So I can simply have the potential energy as I know V, that is 1 over 4 pi epsilon naught Z E over Rn times minus E. That gives me the potential energy to be minus 1 over 4 pi epsilon naught Z E square over Rn. So, my friends, we have this potential energy of the electron. Now that I have derived both the kinetic energy as well as the potential energy, I can get the expression for the total energy. What will be total energy? Say total energy, if I represent En, that will be equal to the sum of the kinetic energy and the potential energy. What did we get the kinetic energy as? Kinetic energy is 1 over 8 pi epsilon naught, right? 1 over 8 pi epsilon naught z e square over Rn plus my potential energy that is minus 1 over 4 pi epsilon naught z e square over Rn, right? With this, now I can simply see that most of the terms are already same, right? Like 1 upon 4 pi epsilon naught z e square Rn, these are same. So if I take those terms common, I have simply 1 over 8 here and minus 1 over 4 there. And that leaves me 1 upon pi epsilon naught z e square over Rn. And this, my friends, we know. So that will be simply En will be minus 1 over 8 pi epsilon naught z e square over Rn. But what I have done is derive the energy in terms of radius of the orbit. So if I don't want that, I can simply substitute the expression for the radius of electron as discussed in our previous video. So if you remember, that was Rn n square h square epsilon naught upon pi m z e square. I can simply substitute this equation here and I get En as minus 1 over 8 pi epsilon naught z e square divided by Rn, which is my n square h square epsilon naught upon pi m z e square. Cancelling out the terms, pi and pi gets cancelled, and that's it. No other term getting cancelled. So I have En equals minus this term will go into the numerator, right? So we have minus m z times z will become z square, e square times e square will become e raised to 4 divided by 8 n square h square and epsilon naught square. So this, my friend, is the expression for energy of electron in nth Bohr's orbit. Again, as you can see, most of the terms such as m, the mass of electron, e, which is the charge of electron, h, which is Planck's constant, and epsilon naught, which is permittivity of free space, they are all constant terms. And 8 is obviously constant. So most of the terms here are constant. So if you substitute those values, you get En is equals to minus 13.6 Z over N, the whole square, and this value is in electron volt. So this expression is quite widely used in solving numerical problems. You should remember this. So from this expression, I can clearly see that if we discuss for hydrogen atom, we know Z is equals to 1, right? So I can say that my En is inversely proportional to n square. That is, the energy of n Bohr's orbit will be inversely proportional to the square of principal quantum number. Now, using this expression, you can calculate the energy of electron in any given orbit, right? Simply, you can substitute the value of n. If you want for first orbit, you can write n equals to 1. And for hydrogen, it will be Z will be 1. We will get En as minus 13.6 electron volts. For any other orbit, just substitute the value of n and divide it by that square. You will get the energy of electron in that particular orbit.